Okay, well, thanks for having me out today. It's always a pleasure to come see you guys at CITA, or south of the border, as we say, because you actually have to go south to get from Detroit into Canada. Little known geographical fact. So anyway, what I want to talk to you today about is the fine-tuning of the universe. So why would you want to go and do that? Well, if you look around us, you see that our universe has the right properties to develop life. We are here, okay? Good. Now, one question is why? Can we say anything about why the laws of physics are what they are? Can we say anything about what determines the laws of physics? Could they be different? Along this lines, many folks have said that small changes in our universe could render it lifeless. And what they mean is that small changes in the fundamental constants of the masses of the particles could make stars not work, galaxies not form, and the universe would die. Now, many of these statements, just to warn you, are made without calculation. So my job, as I gave it to myself, was to say, well, let's do the calculation. And in short, that's what I'm reporting to you today is what is the result of said calculation. Now, this question becomes even more interesting if this is actually real, in the sense that there could be more than one universe. And what we mean by that is there could be more than one disconnected part of space-time, and those different regions of space-time could sample different versions of the laws of physics. One of the things, the fundamental question we'd like to know is what are the possible versions of the laws of physics? So the key question is the universe fine-tuned for life, and by how much? So when I talk about other regions of the universe, I drew you a picture, which is highly schematic. But if we have our universe here, our observable universe is this little disk. This is a two-dimensional representation of a four-dimensional space-time. It's embedded in our universe, which is just like ours. We just can't see outside the horizon. When I go from here to outside the horizon, what do I see? More stuff, just like inside the horizon. But I could imagine going far enough away that I get to a universe that curves and merges onto another one, or perhaps the Big Bang event that led to the launch of our universe led to the launch of another universe. These other disconnected regions of space-time could, in principle, sample the different realizations of the laws of physics, should there be any, right? We don't know, but we could do. We could consider that. Now, one reason to consider that is string theory. I'm not a string theorist. I don't play one on TV, so I can only go so far. But what we think happens in string theory is that there's a whole landscape of possible vacuum states for the zero energy level of the universe. And each one of these vacuum states will give us a different version of the laws of physics. Estimates usually say there's 10 to the 500 or so. That gives us enough leeway to consider different regions of, or parts of, or different versions of the laws of physics. So key questions are then, what version of the laws of physics would allow us to have life, or what fraction of the universes are habitable? And then ultimately what you would like, given the answer to these, is you would like the answer to what is the probability of actually realizing a universe. In order to answer that question, we not only have to know what possible versions of the laws of physics are allowed, but what is the probability distribution for realizing them? We do not know that. So I will say very little about that. What I can do is say, well, how much can I change the universe and have it work or not? Now, let me come clean right from the beginning and admit this is, in fact, a counterfactual exercise, right? So you can take different viewpoints on what we're doing. One way to think about it is, well, I take the multiverse seriously. There really are other regions of the universe, and it's our job as working theorists to explore the possibilities. One can take the anthropic point of view, which says, we're here, the laws of physics had to be such that we could exist, and I will use that as an explanation for why the laws of physics have the form they do. That is, in my mind, at best, a partial explanation, certainly not a complete explanation. Some people love it, some people hate it. It's certainly related to that. In order to make an anthropic argument, you first have to know what versions of the laws of physics work, and that is what our mission is here for today. And the other thing to keep in mind is that we really want to increase our fundamental understanding of how our universe works, okay? If you want to understand how your car works, you take it out on the highway and you punch it and you see how fast it will go. You kind of take things to the limit until they break. So in the same way, we want to take our theory of stellar evolution and take it to the limit until stars don't work anymore. That will not only tell us what range of laws of physics work, it will also give us some insight into how stars actually work. And finally, the fourth region is just, it's kind of a lot of fun to consider these things. So, but the main reason really is our understanding of astrophysics in our universe. So with all this preamble, the outline of the talk is as follows. There are two big questions. One is, what parameters are allowed to vary from universe to universe? And two, given that, what range of values of those parameters allow for the universe to work? Now, I should also tell you guys that I just finished a review on this topic for physics reports that just got accepted. It's hung on the AstroPH survey a couple days ago. It's 200 and some pages long. I will not get through all of the material in the next, how many hours did you give? So we'll get as far as we can. I beg your patience for not finishing. Okay, so let's get going. So key question number one, what parameters are allowed to vary from universe to universe? Now, there's two different ways to view this. If you go around the corner in my department to the particle physicists, they say, well, the only thing that matters is the standard model. Those are the only parameters. And the parameters there are the masses of the quarks, or the coupling constants that determine the masses of the quarks, if you want to say it their way, the masses or properties of the bosons that carry forces, the Higgs particle, and then the corresponding leptons. Now, the standard model, when you put it together, has 26 parameters. We're not going to vary all 26 parameters of the standard model for a couple reasons. One, it doesn't really make sense to do so. Plus, do you really care about the mass of the bottom quark in your everyday life? The answer is probably not. So some of these are actually more important than others. Now, if you're not a particle physicist, but rather an astrophysicist, like I'm guessing many of you are there any actual particle physicists here? You're sort of one. Yeah, okay. So you can live on this side.
Before you go on, would you care about the mass of the bottom if it got into the range of the others? Like if it was just like an upward?
Oh, yes, you would. Yeah.
You would want to vary it if that's a distinct possibility.
Oh, right. No, if you varied the masses of the heavy quarks down to the mass of the light quarks, then you would actually not just produce bound states of light quarks like protons and neutrons. You would have a whole elephant full of different baryons, and that would lead to a very interesting, perhaps habitable, but different universe. I'm not going to go there today. I've actually played a little with that, but I actually don't know what I'm doing enough to do it fully correctly, just to be honest with you.
You won't change a lot today, but if you change it to the second after the Big Bang, then it might change things.
Sure.
So easy to discount.
Well, let's revisit that, okay? I should also remark that, yeah, no, if we discuss each point, then it's not going to be 4 hours, but more like 40. So just to warn you, okay. All right. Oh, that's true. Okay, so if we're astrophysicists, when you run the stellar evolution code, there's not actually a little knob that says set the mass of the top quark, right? What you see in the stellar evolution codes are things like the yields of nuclear reactions, the reaction rates, and so on. So astrophysical parameters are actually not what the particle physicists would call fundamental, but rather composite parameters that depend fundamentally on the four forces of nature that appear over here, but are not exactly the same. Same with cosmological parameters. Also notably absent from the standard model is something called gravity, which is indeed a physical force, but we don't actually have it in the standard model, but we do need to include it. So the two parameters that I think are the most important, and then I'll give you the rest of them in the next slide, is we have the fine structure constant, which is just the charge on the electron, and the gravitational fine structure constant, which is just g in the right units. Famously, the ratio of these is about 10 to the 36 in our universe.
What's m in the right panel?
The mass of the proton.
Proton.
Yeah. You could do it with the mass of the electron and get a slightly different number, but this is standard, okay? So anyway, this is a big number. And one of the questions is, does it have to be a big number? We can put constraints on that, and we will later. So alpha and alpha g are two of the fundamental parameters. If I expand to what I would say are the most important of them, We can also go further if you like. I would define fine structure constants, or the equivalent for all four forces: strong, electromagnetism, weak, and gravity. The ratio of the electron to proton mass, and the masses of the two light quarks. And these are the values in our universe, okay? So in principle, you can imagine a universe where these are the most fundamental things, and you turn these knobs up and down, and you ask what range of those knobs will give you a universe that's working. And we also have to define what we mean by working. What I fundamentally mean by working is one that can produce stars and planets and galaxies and live a while. And I'll try to be a little bit more careful about that later, okay? Now, if you're a cosmologist, you might say, well, those parameters don't actually show up in my cosmological model. I get Q, the amplitude of the density fluctuations at the primordial era, or as measured by delta T over T in the microwave background, which is about 10 to the minus 5. There's a spectrum, but it's about 10 to the minus 5 in amplitude. There's eta, the baryon to photon ratio, which is famously about 6 times 10 to the minus 10 in our universe. That gives us the right omega today in baryons. There's a corresponding dark matter. You can think of it as a dark matter mass weighted mean per photon, which is just 6 times bigger than this because we have 6 times more dark matter in our universe. There's the cosmological constant, which we can write in a variety of ways. If I write it as an energy scale rather than an energy density, the scale that we measure is about 0.003. I'm going to assume that the universe actually has inflation or the equivalent or something to make it big, old, and flat so that I don't have to worry about omega. And then in addition to all these, we have nuclear constants which set the nuclear reaction rates in stars. I will define what I mean by this more precisely, okay? So these are my parameters. I'm going to have very fundamental parameters and cosmological parameters, and I want to see what the ranges of all of these things are. Again, in this amount of time, I'm down to 35 minutes. I'm not going to give you a complete assessment of all of these. I will show you a table of the ranges at the end, and I'm going to give you a flavor of what we use to get there, okay? So we can get as far as we can in the next 30 minutes. So, first up, what values of the structure constants allow for stars to work, okay? Now, when I mean a star to work, I mean a star is a star that burns nuclear fuel, but burns it in a hydrostatically equilibrium manner and doesn't explode like a bomb, okay? So it's got to burn but not explode. So you have to have stable solutions to the stellar structure equations. Well, to do that, what I've done is I built a semi-analytic stellar structure model. I'm not going to go into it because it's a whole talk in and of itself. There's 3 papers on this if you'd like to read them. But it's, to give you the highlights, it's a polytropic model. It has one and only one nuclear burning species, the analog of the PP chain in the sun, if you will. I'm using only the radiative energy transport, just to keep things simple. And when you do this, you would nominally think there's a parameter space of 4 variables for the 4 forces: strength of gravity, strength of E and M, which is alpha, strength of strong and weak. But if you actually look at the stellar structure equations, there's a composite parameter that defines that combines the nuclear forces into one composite parameter, which I'll define on the next page. So we only really have a 3-parameter space, okay? So these 3 parameters, which you can think of as G, alpha, so gravity, electromagnetism, and nukes, that's our parameter space. So before I show you the answer in a couple of slides, think to yourself, how big do you think this is? How much can I vary G by a factor of 1%, by a factor of 10, by a factor of 3 million? How much can I vary G and still have a working star? Same with alpha, same with C.
Temperature is very sensitive, right? The reactions are like T to the 5th, T to the 20. It has to be a very small number.
So you might think. So here's what C is. When you do nuclear reactions in a star, you write the cross-section in this form where you separate out the electromagnetic Coulomb repulsion term, which defines what's called the gamma of energy. You put this in the middle of your star where you have a thermal distribution of particles, and you integrate over that distribution, which gives you a form like this, which depends on Coulomb, temperature, but all the nuclear stuff shows up out front. So the combination of the strong and weak force, along with other stuff, like the masses of the particles, shows up as a coefficient out front. So if the only thing that you care about is whether the star works or not, you just care about this value of C. So first up, if I just use the semi-analytic model of the stars, my main sequence looks like this. You see that if I've assumed that the stars go from 0.1 to 100 solar masses like in our universe. The luminosity goes from like 10 to the minus 3, 10 to the minus 4, up to 1,000,000, just like in our universe. Our temperature goes from a couple thousand to tens of thousand, just like in our universe. So the ranges work pretty good. For those of you who are star people and know the details, you'll notice that my main sequence isn't exactly the right shape. I'm giving away tens of % accuracy here. So if you're a stellar structure person, you're screaming. It's like, this isn't good, okay? But I'm willing to do that because I have an analytic model. And I want to vary these structure constants not by a little bit, but by a lot bit. And you're supposed to guess what the range is. So what is your guess for the range? Quick.
Range in what units?
Well, what factor can I vary G in alpha? So dimensionless units. Factor of 0.01 or 10 to the 12 or?
When you go from hydrogen burning to helium burning, then the power goes from 5 to 20. So I would imagine that it's a factor of 2.
Factor of 2. Okay, you guess. 20? Chris. This Chris.
Yes, 10 to 5.
Other Chris. Okay, here's the range. So if I vary alpha and G by 10 orders of magnitude, up and down, I get this whole plane of parameters. We live here at the star. For the nuclear constant in our universe, I have to be under this curve here. So a fourth of this parameter space is allowed. Now, the answer to your question depends on what you vary and how you vary it. I can vary alpha 100 times bigger and 100 times smaller. I can vary G 1,000,000 times bigger and 1,000,000,000 times smaller, and I still have working stars. Now, if I change the constant C as well, I move this whole curve up and down. So I'm moving C up a factor of 100 and down a factor of 100, and you can kind of see how that works. So if all you want is working stars, the parameter space is huge, right?
So what do you mean by working stars?
Well, I define that. I want a star that has valid solutions to the stellar structure equations, which means that I'm powering it and providing the pressure by the ideal gas law, where the heat is provided by nuclear reactions, and it's in hydrostatic equilibrium, and it's got self-sustained.
Electron degeneracy?
What's that?
Is there electron degeneracy? Is there electron mass being varied here?
Oh, well, I'm assuming that I have to avoid electron degeneracy for there to be a star. In fact, what's embedded in this implicitly is that if you make the mass of the star too small, then electron degeneracy will actually keep the center from being hot enough, which keeps your nuclear reactions from going, right? So what happens at the top of this curve is that the minimum mass for stars gets bigger than the maximum mass for stars. The minimum mass is set by degeneracy pressure because you need so much mass to squeeze the stuff hot enough to burn. But the maximum mass is set by radiation pressure because if you're dominated by radiation pressure, then you are unstable and you don't have stable solutions to stellar structure equations again. So the minimum mass exceeds the maximum mass if you go too far up here, okay? If you go too far to the right here, alpha is so large you get Coulomb repulsion, you don't get nuclear reactions. If you go this way, there's no longer a stellar structure solution and you don't tunnel to produce nuclear reactions. You proceed untunneling, unimpeded, which means you explode. So there's no hydrostatic stable solution to the stellar structure equations.
In our universe, you're also dependent on the maximum mass from general relativity, right? At some point, the adiabatic mix is too close to 4/3. So where does this come into the moon diagram?
Well, 4/3 is the same adiabatic index you get for radiation pressure.
Right, but I'm saying you never get that. But when you get to very large masses, the difference between 4/3 and the actual adiabatic is something that you compensate, right? Special general relativistic effects kick in and cover the gap. So this is why you can't get more than like 200 solar masses. So I'm wondering, where does this limit?
Oh, we're below that. So that because you reach the limit I'm talking about before you reach the GR limit. So I haven't included that. I have not allowed my stars to be as big as what you're saying. So I never reached the limit that you're talking about. We could talk about this later, but let us continue, okay? So, so far so good. But you might say, well, that's not quite good enough. I don't just want stars. I want stars to be hot, and I want stars to live a long time, right? In fact, you want them hot enough to support habitable planets, which in our universe means that the surface temperature better be bigger than 300 Kelvin or so that the habitable zone is outside the star, okay? And in our universe, you might want the stars to live at least a billion years, because that's kind of what all the astrobiologists use for an evolutionary time scale. You can quibble with this, and we'll use a range, but a billion years is a good place to start.
You're varying alpha, you're varying the melting temperature of ice.
Aha. So, you're absolutely right, sir. So instead of using 300 Kelvin and a billion years, we want to use the equivalent of it. So if I vary my chemistry, I want to basically be able to drive chemistry with my surface temperature. I want to find the chemical equivalent of 300 Kelvin based on alpha. And similarly, the atomic time scale sets the tick of the clock. So I don't really want a billion years. I want 10 to the 33 ticks of my atomic clock, which in our universe is a billion years. But if you're changing alpha, what Chris said, okay? Chris is smart. You should listen to him. So when you do that, you're clearly going to shut down or pair off or limit the parameter space I showed you earlier. And here's how you do so. If I vary the lifetime from 1 billion years, I get this middle red curve. If I require it to live for 10 billion years, I get the lower red curve. If I only require the stars to live for 1/10 of a billion years, I get the upper red curve, where I mean the moral equivalent of a billion years given the change with alpha. Similarly, the surface density or surface temperatures are all piled on top of each other here. There's actually 3 lines there you can't see because it doesn't matter. Alpha is alpha. It's exponentially suppressing, so that means that a little bit of alpha goes a long way in the temperature. So you need to be below these curves. Now I'm going to go a little bit faster, so this will be unsatisfying to you. You also want to put on additional constraints. You want your planets to be large enough to hold onto their atmospheres, small enough to be non-degenerate. You want them to be large enough to have complex biospheres. You might want the planets to be smaller than the stars, and you certainly want the stars to be smaller than their host galaxies so you can make them. If I put all of these constraints on this parameter space, I get the following. And you see that the blue line is what I had before for surface temperature constraint. The red line is what I had before for lifetime constraint. The black line is what I had before for you must be a star. The only new one is this cyan line. And that's based on the fact that we can make an estimate for galaxies. This is actually kind of a conservative estimate because it's assuming the galaxies cool promptly, a la Martin Rees. And if you do that, then the mass of the galaxy can only be so big, or alpha could only be so small to get good cooling, and that cuts off this part of the parameter space. What's left is the hatch region, which is either big or small. It's your job to tell me whether that's big or small. It's my job to give you the parameter space that works, okay? So it's a couple orders of magnitude up and down, many orders of or left and right, many orders of magnitude up and down. Is it big? Is it small? It's certainly not a couple percent. It's certainly not a factor of 2. It's orders of magnitude. The other thing you can get out of this immediately is the following. One of the key things that we want to know about in our universe is the ratio of alpha to G, or alpha to alpha G. So if I say how much can I vary alpha and alpha G and still have a working star, I can make the ratio 10 to the 4 times less extreme than in our universe and still have a working star. But I cannot make it more than 4 orders of magnitude different than our universe and still have a working star. So that means that if you have working stars, you must have a hierarchy of gravity and electromagnetism of at least 32 orders of magnitude. It's 36 orders of magnitude in our universe, which may or may not be a problem. For particle physicists, it's a problem. For us astrophysicists, it is. Right? That's just gravity, right? But what we see here is that nothing works, star-wise, if I make the hierarchy less extreme than 32 orders of magnitude. There's another lesson here for us, and that is the following. The fine structure constant must be small compared to unity. The fundamental reason is that stars require quantum mechanical tunneling to be long-lived, stable entities. So alpha has to be big enough to provide a Coulomb barrier to provide tunneling. They also must have sufficiently hot surfaces, which just means this a little bit more strongly. Also, I have to have alpha relatively small to not win against a strong force, so I have large atomic nuclei. If I have alpha too small or too large, I would also have relativistic electrons in atoms, and then chemistry would be relativistic. There actually are bound states, but they would be Dirac states, not Schrodinger states, and the whole thing would be different. And planets would be larger than their host stars if alpha were larger than unity. So there's 6 different regions why alpha has to be small. This is actually good news for physicists, because it means that in any universe that there's physicists, alpha will be small, and then they can understand QED perturbatively. Because if you had to go nonlinear from the beginning, we wouldn't get physics understood nearly as quickly. So there's good news for physicists. So to sum up, and I'm going through this a little bit rapidly, but there's a lot to cover. We have seen that stable long-lived, we've required these constraints, that stable long-lived stars exist. They are long-lived, hot. The planets are big enough to retain atmosphere, small enough to be non-degenerate, smaller than their host stars, large enough for complexity, and galaxies can cool and produce stars, and stars are smaller than their galaxies. For this range, we have the orders of magnitude of parameter space that I showed you, and you have a question.
I'm just curious if you, especially we don't know about planet formation on the total time scale of things, if you consider the things interaction of small-sized grains to even get to those small, non-degenerate planets in the first place. How those parameters would affect.
Oh, well, I guess you raised the following question. Mostly what I've talked about to date is the actual allowing for the structure of objects, planets and stars and galaxies. You're asking, or could be asking, well, can you actually make them, given that they could exist? And our universe does that quite readily. I mean, the problem with star formation is not to make stars, it's to keep it from happening too quickly, right? And that's why we have magnetic fields, in sort of a one-word answer. So I haven't fully addressed your question, to be honest with you, but it is a very important question. So I'm so far implicitly assuming that if I can have them stable, they will be made, okay? But let's come back to that later. So next up, you might not be satisfied yet, okay? Because so far we have stars, they live long, they serve as engines of habitability, but there are 3 important processes that people in this business worry about that I have not yet addressed. One is the triple alpha process that produces carbon. One is the case of stable diprotons, and one case is the case of unstable deuterium. Many folks have claimed, and there's a whole literature on this, claiming that if you change the carbon resonance just a little bit, then you can't make carbon and you're dead. That if you change the strong force a little bit so protons or diprotons are stable, then you can burn through the strong interaction. The coefficient of the nuclear reaction rate goes up by a factor of 10 to the 15, 10 to the 16, 10 to the 17. You might think that would be a problem. People have said that's a problem. They have not done the calculation. They've also said that if you have unstable deuterium, then the universe will fall apart because there's no way to get past that stepping stone. All 3 of those are wrong, okay? And here's why. Let's look at the triple alpha. So the problem is that in our universe, it's illogical. Beryllium-8 is unstable. It's unstable with a seemingly short half-life of 10 to the minus 16 seconds or so. So how do we ever get carbon? Well, what happens is that beryllium-8 is made, it's just that it's unstable. So the middle of stars, after they've gone from hydrogen burning and they've condensed so that they're burning their helium, they make beryllium-8, which becomes unstable, and they make more of it, it becomes unstable, and round we go. But there's always a transient population of beryllium-8. That can interact with an alpha particle and make carbon-12, and once you get to carbon-12, you stay there. So in the about 1950, it was not possible to make carbon in stars. And Salpeter realized, oh, there'll be a transient population of beryllium, we're good. Then they realized, oh, the reaction rate isn't high enough. Then a previous Fred, namely Sir Fred Hoyle, said, okay, I'll fix that. I'll make the reaction rate faster. Done. Then he said, I need a reason to make it faster. And he said, well, I'll invent a resonance. Done. Then he said, well, where does that resonance have to be to work? Well, it has to have a certain energy level. Amazingly, Willie Fowler found that energy level in carbon and then switched from being the physicist he was before to being an astrophysicist, thereby winning a Nobel Prize. So that's the abridged 2-minute history of this, okay? But the problem is that if you change the value of that resonance, which is now called the Hoyle resonance, the claim is that you don't get enough carbon. So to address this question, we're going to actually not use my simplified stellar structure equation, but we're going to actually use a full MESA simulation. Again, in the interest of brevity, I'm just going to go straight to the result. So I had an undergraduate, Luan Huang, who spent a year running MESA, which is a lot of cycles. It takes a long time to run MESA all the way through the alpha elements. But what she did is we got into the guts of MESA and changed the carbon resonance. So you can define a parameter delta E. So delta E of 0 is our universe. I can make the carbon resonance 100 keV bigger, 100 keV smaller. Now you can make it bigger than this range, but this is just the range I'm showing you. Then what she did is for a mass range of high mass stars, turned out 15 to 40 was a good range for her to work on. She calculated the yields for all of those stars and then did a weighted average over the IMF to give you the elemental yields of those universes. So what I'm showing you here are the elemental yields of the alpha elements as a function of this delta E. Blue is carbon. So we are here. This is how much carbon in these units you get per star weighted by the IMF as I just described, okay? If I make the carbon resonance bigger, I get less carbon. But what they don't tell you is if you make the carbon resonance smaller, you get more carbon. You can make this all the way down to minus 300 Kelvin, or 300 keV rather. At that point, then it's no longer energetically favorable to make carbon, so you're out of business. And as you make the resonance higher and higher and higher, you eventually get down to here, which is the 10 to the minus 4 metallicity place, which is what we did. These are 10 to the minus 4 metallicity stars. She did a whole bunch of different things, but I'm only showing you one plot. And this is like thousands of stars and many, many thousands of MESA hours. But the point is that you can raise delta E almost to 500 keV and still get carbon out. You can lower it all the way to 10 to the minus, or to minus 300 keV and still get carbon out. So the range that gives you positive carbon is 800 keV. Okay? Now, along the way, you get various amounts of oxygen. You actually lose oxygen before you lose carbon. And when you lose carbon and oxygen, you get magnesium and neon and silicon. So the total of these is almost a zero-sum game. Stars will make alpha elements. Which ones you end up with just depends on the details of the resonances and the reaction rates. But all massive stars will go through all the alpha elements, giving you some combination of them. And then in the end, the core will be iron and it'll blow up if you're big enough, right? Okay. So we have a range of possible carbon-producing stars, which might be as large as 800 keV. But here's the thing. You can ask the question, how much do I have to change nuclear physics before beryllium-8 is no longer unstable? And the answer is 92 keV. 92 keV is less than 800 keV. That one you can take me at my word on, right? So what that means is that it's easier to make beryllium-8 stable than it is to compromise carbon. And if you have stable beryllium-8, you just burn your helium to beryllium-8. You can make the beryllium-8 into carbon later in the same star, a different star, you don't care, it's stable, right? Now just to show you that that works, I had my postdoc Evan Groves calculate a beryllium burning main sequence for various values of the C, and you get slightly different main sequences, which look a lot like the triple alpha sequence you get in our universe. You can also look at the elements produced in the core versus time. And in this particular simulation, this is just one of many, the hydrogen burns into helium burns into beryllium-8, and the beryllium-8 burns into carbon, and you end up with like a half a solar mass of carbon at the end of this simulation. But the point is that there are wide ranges of parameter space for which beryllium-8 is stable. You can make beryllium-8 easily in stars, and you can make the beryllium-8 burn into carbon in those same stars. So the triple alpha reaction is actually not that much of a problem. The other thing to keep in mind about this is that the reason why that you have this triple alpha problem is that you have a resonance, right? But if you ask yourself, what is the spacing of resonances in a nucleus? The resonances are just excited states. So the question is, what is the excited state spectrum of nuclei? Well, they're typically spaced at about MeV apart. 800 keV is 0.8 MeV, right? The ones in carbon are actually a couple MeV apart. But if you take the allowed range versus the spacing, it's kind of a 1 in 3, 1 in 4 proposition that you'll be near a resonance. So that's not that unlikely a priori. So that's another way to look at this. And even if you change things that much, you can make beryllium 8 stable, as we talked about. So the triple alpha reaction to produce carbon is a concern, but it's not as dire as some folks have indicated. Now let's look at deuterium, okay? The argument is that deuterium is the first step in making nuclei, both in Big Bang nucleosynthesis and stellar interiors. And the idea is that we always first make deuterium, and then deuterium eats a proton to be helium-3. Helium-3 either eats a proton or usually interacts with itself to become helium-4, leaving 2 protons. You know the story, okay? But you need that first step. So it turns out that there's 4 ways to get around this. So here we go. The first way is that if you just want energy, you don't need any nuclear stuff at all, okay? Basically, the pre-main sequence contraction time will just continue. The reason why it's only a few million years or tens of millions of years for stars in our universe is that nuclear reactions set in. If you don't set in nuclear reactions, then the pre-main sequence contraction phase will just continue, and you can have stars evolve for a long time. So here's just some gravity-only stellar evolution calculations, again done with MESA, and you see that you get long time spans where you have nearly constant luminosity just from gravitational contraction. The lifetimes of these are a little short. They're only a few billion years, but that's something, okay? Now, the biggest stars, when they are done contracting, what they do, the smallest stars will reach a maximum density due to the Matzner effect or degeneracy pressure. And you'll reach a constant density, and then the temperature will plummet. The stars that bigger than a certain threshold will keep contracting because they can overcome their degeneracy pressure, and they just get as dense and as hot as they want to be. The boundary between this is the Chandrasekhar mass, which is at 5.6 solar masses, which you'll immediately think that's the wrong number. It's supposed to be 1.4. But there's a factor of 4 in there because this is all hydrogen. If you don't have any nukes, you don't get any helium, you don't get anything else. It's all hydrogen, whereas the Chandrasekhar mass that you know and love, you use A over Z of 2, and then square it to get 4. So the Chandrasekhar mass will be different, just saying, okay? So what happens when I get increasing temperatures and densities? Well, you can get the temperatures so large that it's much bigger than the nuclear binding energies, and you get an explosion. The nuclear physics is complicated, but you can imagine getting some 3-body effects and some nuclei. Once you have some nuclei, you will get some carbon. And once you have carbon, you have something called the Cno cycle. Just to remind you, the Cno cycle doesn't need deuterium. You eat a proton, beta decay, eat another proton, beta decay, eat another proton, all of a sudden you've got carbon. Or you have helium and the carbon back. So you can go through this cycle as long as you have carbon. So just to show you how this works, if I crank the metallicity down to Z of 10 to the minus 8, works pretty good. In fact, you can crank the metallicity down to 10 to the minus 14, and stars still work pretty well through the Cno cycle. So basically, the total amount of carbon you need in a galaxy is sort of 1 planet, and you're good. But there's a 4th way to get around this problem, which we call the triple nucleon reaction. So long story short is that when we were talking about the triple alpha reaction for producing carbon, we had the problem of unstable beryllium. So now we have the problem of unstable deuterium. So P on P will give me deuterium. Deuterium will decay. Now it's 1 step more complicated than the triple alpha problem because the triple alpha problem proceeds only through the strong force. The reaction rates are fast enough. I can just use nuclear statistical equilibrium, and the calculation is easy. Here, what I get is I get deuterium. The deuterium will fall apart in its half-life. But here's the thing. When the deuterium falls apart, it doesn't necessarily revert back to the original protons. It will often break up into a proton and a neutron. Now, the reason why that's important is that the neutron will quickly interact again. No Coulomb barrier, strong interaction to make deuterium again. The neutron, you say, oh, it's unstable. But it's unstable on a time scale. It has a half-life of 10 minutes, which is forever in the middle of a star, right? So you have to keep track of the standing population of neutrons. So I made my postdoc, Evan Gross, add a neutron channel to MESA so you can keep track of the neutrons. And then go through this whole thing. Long story short is you get main sequences. So just to show you the answer, I'm showing you 7 main sequences here for both the Cno cycle at low metallicity and the triple nucleon reaction with different half-lives for the deuterium. So the metallicities go all the way down to 10 to the minus 10 here. And the half-lives go from, this is in decay width of EV, so to orient you, this is 10 to the minus 16 seconds, 10 to the minus 17 seconds, 10 to the minus 18 seconds, 10 to the minus 19 seconds. So you see that for these ranges here, the main sequences look damn near normal, right? If I make the metallicity all the way down to 10 to the minus 14, what happens is that the star actually looks, the main sequence looks like the blue curve almost. Because what happens is that you're burning so hot that as soon as you make the hydrogen go into helium with the Cno cycle, you burn that helium into carbon and make the metallicity higher, and you get back to about 10 to the minus 10 anyway. So the main sequences will end up looking like this anyway. If I make the half-life of deuterium smaller and smaller, these curves continue to decrease until I only have a small main sequence. But I still have a tiny main sequence even when the half-life is like the light crossing time of the deuterium nucleus, which is kind of hard to go faster than that, right? There's causality. So the point is that you will still get some nuclear reactions for this wide range of parameter space. Now, when you're doing the triple nucleon reaction, the lifetimes are relatively low, only up to 1 billion years. So what would happen in such a universe is that the first generation would not live so long, maybe only millions to billions, 1 billion years, but it would produce carbon, and then the Cno cycle would give you more or less what we have in our universe. Now, I'm almost out of time, and I have a long way to go, so let me hurry up. For stable diprotons, what you have to do is you have to crank up the nuclear parameter C by many orders of magnitude. But if I crank it up, I get more parameter space, not less. It's actually easier to burn if I have a higher C. Now you might say, well, what about the lifetime? Well, the lifetime for a given star with a given mass, will be smaller if I crank up the C by 15 orders of magnitude. However, stars will live at lower and lower masses. So the longest lived star can actually live as long or longer than stars in our universe. Now, this was just done with my semi-analytic model. You can also put enhanced reactions into MESA. So just as one example, if you calculate MESA with our universe and calculate the main sequence, the zero-age main sequence, you get the blue curve. Exactly the shape of it depends on what you assume for metallicity and convection routines and whatnot, but you probably can't tell the difference in the width of the line. If I crank up the reaction rate from protons to helium-3 by 15 orders of magnitude, the main sequence becomes this. And you see the highest mass stars have almost the same luminosity. The solar type stars have bigger luminosity in this universe by a couple orders of magnitude, so their lifetimes will be smaller. But the longer lived stars go all the way down to low luminosity. MESA doesn't work down here, but you'll still have stars all the way down to the lower end of the main sequence. So the longest lived stars will live for at least trillions of years in a universe with stable diprotons. So the bottom line for the stellar part of this talk is that stellar structure and evolution is a lot more robust than most people realize. Stars can function over a wide range of parameter space. They have very many nuclear processes, gravitational processes, and other channels available to them to both generate energy and generate nuclei. And that means that they're not really the limiting case in habitability, okay? Now, I only have officially about 5 minutes left, so what I'm going to do for the rest of the parameters is I'm just going to give you the results, and then we'll sum up, and I'll be happy to talk to you at whatever length you like, okay? So one parameter you might care about is the fluctuation level of the microwave background, which is a determinant or a proxy for the density fluctuation amplitude. And we measure that to be about 10 to the minus 5 in our universe, and it gives us galaxies. But the worry is that if you make it too large, then the galaxies will be dense. And the argument goes, if the galaxies are too dense, then stars will get stripped off and you're not habitable. If you make Q too low, then the galaxies will be less dense and they can't cool. So bottom line is that you have to actually put in a structure of a galaxy. So for galaxies of different masses, you will get a fraction of the galaxy that's too dense, and the rest of the galaxy will not be dense enough to matter, and you'll have habitability again. So for galaxies of the range from, let's see, 10 to the 10 to 10 to the 14, the other way, 10 to the 10 to 10 to the 14, these are the survival fractions.
Can you just explain what you mean by too dense?
Excuse me?
What do you mean exactly by too dense? You're describing some time.
Oh, what happens when they're too dense? Oh, the argument is that if they're too dense, then passing stars will strip planets away. Another thing that can happen, which we calculated, is that when you get denser and denser, the night sky gets brighter and brighter. And if the night sky is too bright, then all planets will boil. And the too dense to be too bright is actually almost the same. There's another plot, I don't have it in this slide, but it's in the paper, where you do the radiation version of it. And if I didn't show you them side by side, you wouldn't be able to tell the difference. Okay, so it's about the same thing. The point is that there's a lot of real estate left until you get to Qs of 10 to the minus, we're at 10 to the minus 5 right here. But you're good until you're at 10 to the minus 2 or so. The other cool thing about this is, to follow that up, if the middle is too hot and too dense and too bright, and the outside's just like us, there's actually a zone in the middle where the night sky is as bright as our day sky. And in this habitable zone in the galaxy, all the planets, except those that are right next to their star that are too hot, all the planets are habitable because the background radiation provides the light. And the cool thing is that if you choose Q to be about 10 to the minus 3, couple times 10 to the minus 3, you can actually engineer galaxies that have more habitable planets in this habitable zone than our galaxies have, okay? So this just concludes that. Another thing you might worry about, what happens in Big Bang nucleosynthesis? If I vary alpha, if I vary the weak force and vary the neutron lifetime and so on, can I make it so that the universe dies? Now, the only way to die during Big Bang nucleosynthesis is to process all the protons into helium or heavier things so I don't have any protons left, so I don't have water. So is that really a danger? Well, here's the standard result. This is helium, deuterium, helium-3, and lithium. I'm going to use the same colors. And this is the range that we think our universe lives in based on what we see. But you see that if Eta were bigger, it's fine. If Eta were smaller, it's fine. But we just happen to live in this little band, right?
Make heavier elements if you change parameters of physics.
What's that?
Why can't you make heavier elements?
Well, you could if you change things enough. But
How much do you need to change to make fire?
oh, you actually have to change things a whole lot because Big Bang nucleosynthesis happens very quickly. So you're only at hot temperatures for a minute, literally. And
The reason is you limit it is because you don't have stable elements with atomic numbers of 5 and 8.
no, even if you put those in, you have something called Coulomb repulsion. And the helium on helium is going to repel each other a lot. So you need a hot temperature to ever get helium on helium to fuse into anything. And it takes a minute to make the helium, and by the time you've made the helium, it's too cool to go to the next step, right? So you're going to be out of business. Now you can turn things up and eventually get it to do that. And actually my postdoc, Evan, who's no longer my postdoc, is trying to do that calculation in detail, but it's really hard to go beyond that, even if you have stable A equals 5 elements. People say that, but people have never calculated that to show it to. It's another thing that everybody knows that's not true, right? So just to illustrate two of the parameters, if I change eta and G, these are the contours of protons left behind. So these are hydrogen contours. So we live here. I can make eta orders and orders of magnitude larger and G orders and orders of magnitude larger, and I still have 10% protons. I still have 10% hydrogen left for water. It's really hard to kill the universe, to burn everything from protons into stuff. You have to make eta huge and G large, or the strong force super different from our universe. So it's really hard to kill things. Now I'm really out of time now. Just to highlight, the cosmological constant can actually be 20 orders of magnitude larger, and we're still good. It can be 20 orders of magnitude smaller, and we're still good. If you look at the alpha beta plane, you get a few orders of magnitude, and I don't have time to explain this. If you look at the alpha strong plane, you get a few orders of magnitude. And if we have the light quark mass, we get several, or about an order of magnitude this way and a couple orders of magnitude this way. So the bottom line is that for all the parameters I showed you at the beginning of the talk, the quark masses, the force coupling constants, the cosmological parameters, there's a range of decades that are allowed. So just to sum up, the quark mass has about 3 decades. The down quark mass only has about a decade. Beta, the electron deposited ratio, you can vary by 5 orders of magnitude. The difference between the up and down quark, you can only vary by about 1 order of magnitude. The force constants can vary by 3, 4, 6, and 10 orders of magnitude. The fluctuation amplitude can vary by 4. The baryon to photon ratio can vary by 6. The vacuum energy scale can vary by many, many orders of magnitude. Now, we use the term fine tuning, which brings to mind the idea of tuning a radio. But if you actually want to capture a radio station, you have to know your frequency to about 1 part in 100. So that works out to 0.0043 decades for AM radio and 0.00087 for FM radio. So if you compare these numbers to these numbers, you might want to have a change of what we mean by fine tuning. In other words, it requires a lot more precision to tune a radio than to tune a universe. So the bottom line is that the tuning of our universe is not as extreme as some folks have previously suggested. And what I mean by that is that a wide range of parameter space allows for working universes. And what I really mean by that is that this range of parameters allows for working universes. Now, if this is still too small for you, then we're still fine-tuned. It's still small. All I'm saying is that these are the ranges that you want to put on the table. And the other thing that we find is that there are many different astrophysical pathways that show up. If you make deuterium unstable, you have 4 different ways to make energy. That's not what the sun does. If you make the strong force different, you might, and hence change the triple alpha resonance level, you might get different mixes, but you'll still get carbon. You might get stable beryllium, and you don't need the triple alpha, and so on, and so on, and so on. There are many different pathways that the universe has to do its operations. The other thing that I would like to suggest is that our universe is not necessarily the best one. So if you're starting from scratch and going to design your own universe, would you do it this way? Now, let me give you some suggestions, okay? You can imagine a more logical universe would have larger Q, the density fluctuation amplitude. For those of you who do inflation, it's actually, I think you'll back me up on this, it's actually easier to get an inflationary theory to give you bigger Q than smaller Q, right? Yeah. So it would be more natural to have larger fluctuations. If I have larger fluctuations, I can even have habitable zones in galaxies and more habitable planets, which you might think is better, right? So I can have more habitable planets. A logical universe would have stable beryllium-8. If you look at our universe, what are the most common elements? Well, hydrogen and helium. But beyond that, it's carbon, oxygen. Then what? Neon, magnesium. What do these have in common? They're all alpha elements. The alpha elements rule the universe, except for some reason, this guy is missing. The 2 alpha element is not there. So if you had a logical universe, you would just build up alpha elements and you would have stable beryllium-8. And that's a smaller change than it requires to compromise anything in stellar astrophysics. You also could imagine a better universe if you, even though you can get away with a larger vacuum energy, you might imagine a better universe would have smaller vacuum energy. Then I could have more structure. I could have more continued structure. I don't shut off my structure as often. If I make it small enough, I can have larger and larger and larger and larger things continue to come into the horizon in the future. What I happen to be talking about tomorrow night. And that would give you ever larger structures, which could give you more possibilities for habitability and whatnot. It also could be argued to be a better universe. And all of these things could lead to more stars, which could give you more opportunities for habitability. So I'm out of time. I'll be happy to stay and ask questions. Let me close by, first of all, acknowledging my people. Evan Gross was my postdoc for this. Alex Howe is another postdoc who was not mine. Lillian Huang and Kate Koppas were undergrads working on this. And Tony Block is a math professor who helped on this as well. There's a whole series of papers that we wrote from our group on this. And this culminates in the review, which is not yet out on Physics Reports, but came out on AstroPH 2 days ago, just in time for this talk. So this is kind of the launch talk of that. So you guys are the first people to see this after the thing was launched. So anyway, let me shut up here, and I will take questions. So.
Thank you very much for the captivating talk. So the question is there.
Maybe this was touched on in the table, and I just don't think about this enough to interpret the table with the different parameters. This is something I thought about a lot when I was studying for my qual, so I apologize for the students who are studying for your general qual, and the fact that they're concerned with my demos asking this question. How different would our universe be if the mass ratio between the proton and neutron was swapped? Considering the early stages of Big Bang nucleosynthesis, how much does that factor into the evolution of our universe? I don't know if you've thought about that.
Well, there's a couple things. I kind of went through it too quickly. If you change the quark masses, then you will change the masses of those composite particles. If you change them too much, then you can get processes that kill the universe. The easiest one to explain, which is also the most constraining, is that in our universe, it's not energetically favorable for a hydrogen atom to spontaneously turn the electron and the proton into a neutron. But if you change the quark masses enough, that could happen. So that's the killer. In Big Bang nucleosynthesis, there are pockets where if you change proton abundance or neutron abundance, you could imagine the universe could get too processed. To give you one example, people have considered what they call the weakless universe, which I didn't have time to talk about. But if you have the weakless universe, then you don't have the weak interaction at all, and then you don't have neutrons decay, you don't have beta decay at all. Then you'll go into Big Bang nucleosynthesis with equal amounts of protons and neutrons. In our universe, we go into Big Bang nucleosynthesis with about 1/6 as many. That's sort of the canonical number. And then over the course of the next 3 minutes, it decreases to about 1/7, right? That's what you learn in your early universe cosmology course. But there's a difference between 1/6 and 1. Because to 0th order, if you want to get the yield of helium out of BBN, you just say, well, all the neutrons end up in helium, and I had 1/6 of them or 1/7 of them to start with, and I put them with the protons, and I get 1/4 helium, and it works pretty well. And it's actually not a bad approximation. But if you had equal numbers of protons and neutrons, then all the neutrons would combine with all the protons to make helium, and you have no hydrogen left over, no water, right? So that's one way that things could go. So the weakless universe is a manifestation of that. But here's the deal. You still need time for those nuclear reactions to take place. And time depends not just on the evolution of the universe, but also on the density of the universe. N sigma v, which is the reaction rates, depend on n, the number density. So if you take the number density of particles, of baryons in our universe, and you shut off the weak interaction entirely, which means you have equal numbers of protons and neutrons, then you will process 99% of the stuff into helium and not protons, and you'll kill the universe almost. But if you just make an order of magnitude smaller, you're fine. And if you make it about 30 times smaller, you get the same yield that we get. So there's two lessons here. One, I have thought a little bit about what happens if you have too many neutrons, which was part of your question. We can talk more about this later. And two, it's hard to kill the universe with BBN. There's other knobs you can turn.
There was one question here, but
Well, a couple of related questions have to do with the chemistry of life. Water has liquid water has remarkable properties, solubility and so on. So you would want water to some similar molecule that retain that property. And secondly, you have lots of beryllium. That's going to change the chemistry of life almost.
Yeah, if it stays in beryllium, then you'll have lots of different chemicals around.
But
Yeah. So one thing I can tell you about your first biochemistry thing, since I just wrote the review on this, very little work is being done on molecules, which is what you're talking about.
chemistry for all these.
You have to redo, yeah. So whereas the physics is kind of well enough developed that I could write a 200-page review on it, the chemistry and molecule part of it is a 3-page appendix in that, because that's all there is. There's like a couple of papers. Now, what they have found is that you can vary alpha, and if you vary alpha, what you will do, like in a simple molecule, like they can really only do hydrogen molecule, which isn't like super satisfying for biochemistry, but it's a start. But what they can do is they can vary alpha and vary the length of the bond and whatnot, and see how changes in alpha change the bond. And you can also then extrapolate that to DNA and say something like, well, if DNA has to work, you basically can't change the ladder spacing by more than what? There's some number like 15%. I don't remember the exact number. And then you can say, well, alpha, do you need to change bond lengths by 15%? And it's, 15, 20%. Yeah. Right. You could imagine that if everything is just scaled down by 5%, who cares? It would still match up, right? So
some things care a lot, right? If you drink heavy water instead of regular water, you don't have subdivision. So
that's because no, but that's not the point. The point is that heavy water changes the bond length, so heavy water doesn't work in our universe because our universe is engineered to not use heavy water. If you imagine a universe where you shrink all the bonds by the same amount, they could still match up. You have to start, like Chris was saying, you have to do the whole thing from the ground up. And there's only a couple papers written on this, and it's really in its infancy. So I can't give you a satisfying answer. I'm sorry. But it's something for you to go home, go back to your office and let us know, right? Oh, okay. No, it's a complicated problem. George Ellis has written a couple of the papers on this, so he started to think about this. And George Ellis is a very, very credible sort. So, but he hasn't gotten that far because it's a hard problem, as you were saying. So, there's another question in there.
You guys explored neutrinos, microplanes, masses, or the properties of those?
A little bit. In our universe, if you make the neutrino masses too large, then they'll start to affect structure formation. You have to make them pretty large before it matters. I mean, you could like change the details of structure formation so that the halo mass function doesn't look like our halo mass function, but that wouldn't be like disastrous for life. You'd basically have to make the neutrinos as massive as what we think the cold dark matter density is in order to sort of change the universe substantially in that regard. The other thing that neutrinos do, we were talking about this at lunch, they are allegedly an agent of making supernova go off. So the lore is that you want your neutrinos in a massive star explosion to be just the right amount of optically thick. If you make them too optically thin, all the neutrinos escape immediately, and you don't have the neutrinosphere to help push out the shock, and you'll get a failed explosion, just a black hole. Similarly, if you make the neutrinos really, really interactive so that they interact in the core, they never get out to push out the shock, and they still get stuck in what becomes the remnant. So there's sort of a sweet spot where you need the neutrino interaction to work. We don't know supernova well enough to know what that is, but it's factors of 2-ish in interaction rate, or G Fermi, or whatever units you like to work in. But here's the deal. If you shut off massive star type 2 supernovae, there's a whole elephant full of different kinds of supernovae, including 1As, that also give you heavy elements. You won't get the same suite of heavy elements, but if all you want is carbon and the things that are the most important things for life, that's the bottom part of the periodic table. You could imagine that. You might like mess up all the R process elements. Things could be very different at that end. And again, this is not fully worked out, just so you know. This is kind of the lore to date.
Okay, so if there are any more questions, let me make a suggestion. Let's thank the speaker once more time, and let's take the question up separately.
Okay.